Okay. Uh, okay, everyone, welcome. This is the third week, the third lesson for the Android Beginners course. I'm Erwin. I'm the tutor for this course, and we'll be talking about a little bit of things that happened on this lesson. First of all, in this lesson, we learned about custom views. We learned about threading. Threading is really important in Android, and most of it comes from the class Java. Of course, as Android comes from Java, and we learned about some loaders and ways to handle the data. We learned about custom views and some navigation problems that may occur. And the thing is that uh, um, I like to talk a little bit about how trading works, some of the problems, and some a little bit about services and the different things that may happen when you select one option or another. You know, a 100 thread or an async task. There's even a couple more options than that. There's a thread pool executor and intent services. And I'll mention them briefly in today's presentation. Okay, so now let's start on this presentation. And let me just okay, here we go. So for the course, as I mentioned earlier, the course talks about trading and services and how to handle and pass data from one thread to the other and how to handle that data. Some good design choices and some stuff that may be of interest when doing a thread, like working with an API, like the example of the exercise of the Girl API, where we use a background thread to continuously handle the calls to the API, so the main thread will be free and will not freeze or stop responding, because that's one of the most important things when you have to consider when building an app, and that is avoid the freezing of the application, because if an Android application freezes for more than 5 seconds, you'll get that message of application. Users see that message and quit the application. Maybe the application is working, but the message is just to let them know that there is too much work going on. But users don't care about that. They'll think the application is frozen and they think, it stopped and it doesn't work. So they'll close it, and maybe it just need a little more time. And basically, that's the important part of trading. In a small app, think of the lesson one app, the tip calculator. There is really no point of doing that on a background thread, but on more complex applications, like I mentioned, the APIs, it's really important because otherwise the app will freeze. Games really have probably the most use of threads, because if they don't use threads, there is no way they will be able to handle everything that is happening. So, and like, this is what I've been talking about, threading. On Android, we know the MainTrail handles the input events, the rendering, the UI, and basically everything has to go over the main thread, right? And by default, Android doesn't use threads. It just uses the UI thread. And this thread works like like a Java thread. There's really nothing hidden about it. It's just a thread that is handling the events. And as I mentioned a little bit earlier, slow and unresponsive apps is really a big problem when developing. And the thing is, threading can solve many of those problems. And that is because, of course, the main thread should be focused on rendering the UI, not on working on, for example, making a calculation or fetching data. That isn't work for the main thread unless it's really, really small. Like I said in the tip calculator, there is really no need to move that to a background thread. And one type of thread, really the simplest thread, is the async task, where it is that async tasks are good for short operations, and they really don't need an UI. And that's a really good advantage, since we can just throw work at it and then wait for it to return. But you also have to handle the callbacks. Remember that on pre-execute, on post-execute, and all those callbacks, you can handle them and know what data to move from and to the thread. But you can cause some problems with this. You know, a sync task on post-execute can operate on the main thread, but that can be a problem. Think of this. Sync task runs on the background, right? We throw some work at it, and then we decide to load another view. Like, think there's a second fragment, and the application and the user decides, I want to use the other fragment while this async task is working. We have to be careful about working with background threads, because if the second fragment is loaded and the thread reaches post-execute, it will probably try to post that to the main thread, but there's no reference to the views that async task was working on. If it's updating a list and the second fragment doesn't contain the list, it'll basically be lost work. You know, it's just using memory and using resources. And the other thing is that a thread can have, you know, like if it's gonna post on a list, it has a reference to a list, and that list contains a reference to the activity. So a thread contains a reference to the activity that called it. And that means on memory, the thread has another block of information for the activity. And if that thread doesn't do anything because it lost its references, then it's just using a lot of space. And the final thing is, async task is a background thread, but it's not like a real parallel thing. The thing is that it's all calls to a sync task work on a same background thread, meaning that if you try to throw like 10 async tasks to do background work, they will all go on the same thread, and that is really not what we want, because it will just be slow. And for example, think there's a job that will take forever to complete, like it's running a huge query on a database. Then since they all work on the same thread and they execute serially, then the async task is prone to being stopped. And that means that the async task will not, for example, the next async task will have to wait for the large async task, and that will take a lot of time and it's really inefficient. So async tasks, that's really a reason that we don't have to use long operations, but we also don't have to use many async tasks, because we will run into the same problem. Okay. The other thing was handler threads. They are a bit more robust, and they are designed for long-running operations. And the thing is that a handler thread is made up of three things, right? The loader, the handler, and the thread. The handler takes, well, first of all, the handler thread works on a queue of tasks. Like those are the messages that they receive in the example of the lesson. Eh, the handler thread is meant for receiving many messages over time, and then the handler takes the messages from the queue, and well, an application sends the tasks to a queue, and then the handler takes the queue and sends it to the loader, so loader can load, well, not loader, looper. The looper can actually do the work that the thread is meant to do. And this makes it a bit more complicated than a syntax, but it's really more robust, but it also uses more resources. So that's why we don't want to use a handler for a small task. It'll be using too much resources for something that doesn't need it. One of the things is that we have to handle messages and callbacks. Like when it receives a message, we have to decide what to do with that message. We have to decide what to send back, what to operate on it, and there's really a lot of work inside this class. And one thing is, the main thread uses one of these kind of threads for separation. It's just that the queue of the main thread is mostly compromise made up of tasks that are update the UI and reading input events, but it's basically just a handler thread. Now, some other things about threads. Threads cannot like their colors, meaning I talked a little bit about the syntax having a reference to a fragment that is no longer visible. And this can happen on any activity that may get destroyed. You know, for example, if we have an activity running a thread and the phone rotates, the activity will get destroyed, but the thread will not. The thread will still keep running. And then when it rotates, it may start another thread. So we'll have two references to the same job, but one of them is just holding memory. And this is something that we have to consider, because if it's taking too much memory, it will be processing too much. And then, a user can see which applications are draining battery or are using too many resources. So if our application is not careful with this kind of memory leaks, the user will just decide to install it. And nobody wants that, right? So back on the example of the syntax, think that we throw two different threads to the same reference, for example, the same list, and say both of them want to update. At least maybe one is trying to update an object and the other one is removing objects, right? Maybe it's filtering data. So what if two threads have a reference to the same object? We have thread A trying to update the view and thread B that is going to delete the view. And this again causes the problem of needless work, because if they happen at the same time, imagine it will update the view, but then it will be removed. And that really benefits no one. Since the user won't see it and they will have no time to interact with the view that just got removed. So, as I said, it will do pointless work. The threads basically just, one of the threads wasted its time. And it can also result in memory leaks. Again, it will just stay on memory, wasting space, since maybe the exit condition of the thread was linked to a view or an input event of the activity, and that activity is no longer has that view. Like maybe it's reading data until you press a button to stop, but the other thread already removed the button for some reason. And so that other thread will just keep reading data on the background forever since it had no exit condition. And of course, this has always been a problem, memory leaks. But we have to be careful. It's slow to the app, it runs better because it's using the processor. It may even crack the apps, right? So imagine if it has a reference to an activity, a strong reference, because there are also weak references that just get deleted. Maybe it tries to do something in the UI and the application is no longer there, so it will crash it. And this is one of the reasons that threads don't have to interact directly with the UI, right? Because it may crash. Or also maybe if it's using too much memory and the thread just keep going and going, the app will run out of memory and it will crash again. Using a loader can solve some of these things, because a loader just receives the data and makes sure it reaches the activity or the view that it's trying to reach. So one common cause of a memory leak using an async task. This is an easy way to understand how an async task works. But the problem is that here it was declared as an inner class of another activity. The problem with this is that the inner class has a reference, an implicit reference, meaning that is a reference that is there but was not declared. It has an implicit reference to the main activity. That means when it's created, it will reference the main activity. And we'll run into the same problem I mentioned before. The activity may get destroyed, but the thread still has the reference, so it will keep working on the background while still containing the activity. So it will just use a lot of data, a lot of memory data. The solution is simple. Declare the async task as static. And a static class doesn't hold reference to the instance of the class that is contained in. It's really simple, but in the long run, it can be really problematic. Now, intent service. We learned about services in the lesson, right? Using a service to it was on a previous lesson with the broadcast receiver and sender. We send a service to alert the broadcast. Services can work as pieces of, of the application. It can handle some logic. It can run its own processes, but they are a bit complex. We have to manage everything about a service. When it's called, what it's doing, we have to manage its life cycle, and we have to tell the application when it has ended and what cleanup it has to do. So a normal service is a little bit complex. And the other thing is, service runs on the main thread unless you tell it to run on a background thread. So it's a step to take, and it has to use another method of running on a background thread. For example, we have to use an async task or something declared on the service to make it work on a background thread instead of the main thread. So, of course, it also handles its own lifecycle. Intent service is it's a kind of service that also implements a handler thread. So it's kind of a combination of the two things. It also handles its own life cycle. So this might be more useful to use now than a simple service, because you only have to worry about one thing, and that thing is what it does and what to do when it's finished. It works of a task queue, of course, because it's using a handler thread, and so it's working at you, so it handles one thing at a time. A service might use another, well, a regular service might use another method of threading, so it may be able to do some parallel work. But that's kind of a trade-off, right, between both kinds of services. It, it stops when it has nothing else to do, so it kind of does its own cleanup. And this is the things it needs a constructor and what to do. Of course, we have to be sure to send the message when it's done, probably through a receiver or a local broadcast receiver. But the important thing is to send the message. And that's one of the things intent service is good for. It handles itself pretty well and it's really easy to use. And when complete, of course, it can also call the run on UI thread method, and that runs the, the, the thing that it wants to send to the main thread on the main thread. Oh, well, I also want to talk about this thread pool executor. It's not really explained on the lesson, but it's because it's really not gonna be really very common to use it, but it's another way to use background work. It works on huge tasks that are made up of simpler or that can be divided into simple, smaller tasks. Like, for example, think of it reads a huge list, like think thousands of entries, and we want to know how many times a particular letter is in those lists. We can, well, the thread pool executor creates a lot of threads, and it can pass bits of data to each one of them. So each thread can operate on the data and then just return a result. It's also good for applying a filter to an image. Think of the camera apps that offer this functionality. They can, for example, think a 10 megapixel image. They are huge, and trying to run that on a single thread will just take so much time. Using a thread pool executor, we can throw many little threads and throw each one of them a little piece of the image, and then they will apply a filter to that piece and return that piece with the filter applied. Then we can just combine everything, so we avoided a lot of work that may freeze the background thread or even the main thread if we are running there. The thread pool executor can change the amount of threads it needs based on the size of the job. So it's really good for this kind of things. Like maybe one image is really huge, but the other one is not so big. So it can adjust the number of threads to make sure that it's using a better performance. You know? And this is because threads aren't free. Declaring a thread costs memory, even if it's not doing anything. So we have to be careful with this too, because we can also make a thread pool executor on many threads as we want, but there will be a point where all the threads will just use the memory only by existing and not doing any work. So the other thing is scheduling. Maybe we don't want to run the code right now. Like maybe there is a problem with the conditions or the time we're trying to run. Maybe someone is running on their mobile phones, right? And they are using mobile data. Think uh, we want to download an update. We received a notification there's a new update, and we want to download it, but we don't want to download it on mobile data because that's limited. We want to wait for a special condition. Or maybe we're using a planner app where a user makes a plan for, say, 8 p.m. or something. Then we want to run the application on that exact time. And well, there are a couple of ways to make this. The first is Alarm Manager. It runs at precise times, meaning we can set exactly the time we want, and that's the real most relevant use for the Alarm Manager, running a piece of code on a specific time. That is because it has been replaced by JavaScaler. JavaScaler replaces Alarm Manager because it has many features that makes scheduling jobs easier. It runs on certain conditions and not on only times like the Alarm Manager. Of course, we still want to use the Alarm Manager for this, for running at the specific times, but because the job scheduler runs on conditions, and job scheduler also batch runs its jobs. Like we have 10 jobs at 8 p.m., but the system is already batching another job for like 801 maybe. I don't know, but the thing is that JobScaler will try to run every job together to save memory, to avoid waking the phone, and to avoid waking the phone for running a job is one of the main causes of battery drain. So the JobScaler will try to run them together to avoid this kind of behavior. It also has some control over certain conditions, like the scaler will be able to run, like I said before, if the user receives the notification on mobile data, it will not run on mobile data. It will run, you can set it to run when it's connected to Wi-Fi and not data. We can also set it to run when it's charging. Maybe it's a really important update, like a security update. And the thing is that JavaScaler also runs on the MainTrail, and that's a problem we're trying to avoid the whole lesson, running on the MainTrail, because if the JavaScaler job is just sending a notification like maybe your appointment is late or something, it'll be very fast. But if it's a huge download, running on the MainTrail will just freeze the app. There's no way around it. JavaScaler allows to actually define if we want to run on the MainTrail or not, and that's on the return parameter of the JavaScaler. I will not be talking much about this, but know that JavaScaler can run on background threads, and you can also tell the system, the application, if this job is really important and it gets interrupted for some reason, it will reschedule the job and run it again for you. You don't have to handle like there was a connection error and the download didn't finish, so you have to reschedule. You just have to tell the job scheduler to reschedule for you. And that's about it. I want basically some things to consider is that memory is limited, and using threads can increase performance for the application, but then it will also increase memory and it will increase battery drain, and sometimes it will not even be a benefit. If we're working too much, we're making too many threads, the threads, if they're async we run one after the other. And that's really no benefit of running them on the MainTrail. Well, except not blocking the main thread. But the point is that you have to choose the right background service. Like the job scaler can run it on a schedule that you set on a condition. Maybe that's something you want. The async task is for small jobs, but you have to be careful about references and not having memory leaks. You can use loaders to handle that. But of course, mix and matching all these things maybe will have a lot of code and will be a bit complicated, but on the long run, on big applications, is really worth it. Trust me. And handler threads work on a queue, and the thing is that they are a bit expensive, and if, for example, we have it running forever, but the queue is empty, it will just be there, wasting space and memory. Okay, now I wanted to talk about the exercise, about the async task of the P3 exercise is this, using async task, right? Really, the only thing I can tell you about this, it's really simple. It's just mm, running the code that posts the API into the thread and then post the results on the main thread on the UI. Excuse me. It's a really simple exercise, but remember the things about the syntax. You have on pre-execute. We don't use it right here, but pre-execute can set up the environment or maybe show a progress dialog where you are reading the needed information for the thread to run. Doing background is the actual thing that we want to run, and it's a reason we'll call an async, right? Doing background has a publish progress a method that we can call to, well, publish the progress into the UI thread, and you'll do it by calling this. When you call publish progress, it will call on progress update. That it will let the main thread know that there is something happening. Maybe it will show a progress bar or some numbers, or maybe we'll display a piece of the image that it has been loading. And finally, the on post execute is the result, what we wanted to do. And this one runs on the UI thread. Again, you have to be careful about running on the UI thread. Using messages and loaders may be a bit complicated, but it's really important that you don't reference stuff that is not there, because it will be memory leaks, and memory leaks are bad. That was basically the whole point of the conference. Well, that was the whole presentation. So thanks for listening. And if there are any questions about the lesson, the exercises, or any of the small quizzes, right, you can ask them right now. Hmm. No, well, okay. Well, thanks for listening, and we'll see. We'll see you the next week on the presentation for the lesson 4. I hope you learned something about it. It's design considerations that we have to follow if we really want to present the best possible app. And it's there's really no enough time to talk about all these things. Android and Google especially makes really good documentation and examples, so you can read about all these things if they interest you on their pages, the developer page or their YouTube channels. They have really good tips, and they're well. Thanks for staying with me, and I'll see you the next week.